Hi, welcome to Algebra 2 Common Core. Today in lesson number 5, we're going to use the log rules that we were just introduced to in the last lesson to then solve equations by condensing the equations first. So let's first recall what those rules of logs are. Please pause the video for a minute and see if you can write down the 3 log rules that we learned yesterday. When you're done, come back and we'll go over those 3 rules. So the first log rule has to do with taking the log of a product. So if I've got, for example, the log of m times n, remember that we have a product after our log, so that means, because these really stand for exponents, we are going to rewrite this as the log of m plus the log of n. Our second log rule is our quotient rule. So the log of a quotient, m divided by n, is just equal to the difference of the logs, log of m minus log of n. The third log rule is our power rule. So log of m raised to the p is just equal to p times the log of m. Now we're going to be using these rules today in the condensed direction, so that means that we're going to be starting with the expanded version like this, and we'll be condensing so that we just have one log, possibly on each side of our equation. So now let's take a few minutes to write down the steps that we're going to need in order to solve log equations using those log rules. You might have to pause the video if I'm talking too fast or if you can't write everything down. So please make sure that you write down all 3 of these steps. Step number 1 is going to be to use the log rules to condense each side of the equation. So some of our equations will have logs on both sides, some will only have logs on one side. Use those log rules and condense so that we only have one log on either one side or both sides. Step number 2, if there is only a log on one side of the equation, then we're going to rewrite the log equation as an exponential equation. That will help us to be able to solve the equation, so we won't have any logs in the equation anymore. The third step, which isn't really a third step, it's a second step, because if instead of having a log only on one side, we have logs on both sides of the equation, then what we're going to do is drop off the logs and solve the equation. That's because if I've got a log on the left and it has to equal a log on the right, then the argument of each log must equal each other. So let's try a few of these practice problems. For the first one, we've got log to the base 2 of 2 plus log to the base 2 of x minus 4 equals 5. Now, admittedly, there are several ways to solve this log equation, so you may be thinking to yourself, oh, I know an approach that I could use for this. If that's true, go ahead and give it a try. I'm going to use the method of condensing. So to condense this equation, I see that I've got a sum between 2 logs. So our log rules tell us that whenever we have a sum between 2 logs, we can rewrite this as the log to the base 2. You'll notice that both of them had to have the same base. They both had a base of 2. So by doing the condensing here, I'm going to take the argument of the first log, 2, and I'm going to multiply it by the argument of the second log. So we're condensing so that we only have one word log in this new equation. But this equation is equivalent to the original one that I had. Now that I have a log on just one side of the equation, and it's just a single log, I'm going to rewrite this as an exponential. Remember, I like to use the arrows, so I begin at the base, I raise it to the answer, which is going to be our exponent, and I set it equal to the argument. So I'm going to rewrite this as 2 to the 5th power is equal to 2 times x minus 4. So by doing the exponential form of this equation, I've eliminated the log, so I've made it a much easier equation to solve. 2 to the 5th power, we know that that's 32. If I distribute 2 on the right side, I've got 2x minus 8. So to solve for x, I'm going to add 8 to both sides of the equation, so I have 40 is equal to 2x. And of course, if I divide both sides of the equation by 2, I see that my answer is x equals 20. Now I'm going to take a look at the check for this one because it actually is a really good practice with solving logs. So over here, let's do our check. So I'm going to take my original equation and I'm going to replace the x with a 20. So I've got log to the base 2 of 2 plus log to the base 2 of 20 minus 4, which is 16. Does that equal an answer of 5? Well, we hope so. We think we have a solution. Now I'm going to do this by looking at each log separately because by now we should know how to get an answer for a log. In the case of the first log, log to the base 2 of 2 means what do I have to raise the base of 2 to get the argument of 2? And of course I know that that exponent has to be a 1, so the answer for the log is 1. For the second one, what do I have to raise 2 to get an answer of 16? I know, of course, 2 to the 4th is 16, so that means the answer for that log is 4. I do see that 1 plus 4 is equal to 5, so that solution of x equals 20 does check in my original equation. Now I'm not going to do the checks for all of them, but that was a very interesting one to take a look at so that we could practice again with evaluating logs. Looking at example number 2, I've got log to the base 9 of x minus 2 plus log to the base 9 of 8 is equal to 1. So again, there is a sum of 2 logs. So when I have the sum of 2 logs, I'm going to rewrite this. I'm going to condense the logs into log to the base 9 of x minus 2 multiplied by 8 has to equal the answer of 1. Now I see that I only have a log on the left side of the equation. So if there's only a log on one side of the equation, I'm going to rewrite this as an exponential. Begin at the base, raise it to the answer, which is the exponent on the log, and set it equal to the argument. So 9 to the 1st is equal to 8 times x minus 2. Of course, we see that x minus 2 times 8 is the same as 8 times x minus 2. So let's solve this for x. So 9 is equal to 8x minus 16. Add 16 to both sides, so 8x is equal to 25. And this one is a rational answer, but not quite as easy to check as the last one that we had. So 25/8. So I'm going to say here is my solution. Now, if you've got one of the TI-84 calculators, take a look at that calculator and see if you can find on the calculator where you can do a log to any base that you want. Because if you do have that on your calculator, you would be able to store this value of 25/8 and then type in the left side of this equation with a base of 9 and see if you get an answer of 1. We'll talk more about that in class tomorrow. Let's try another example at the bottom of page 9 in your notes, example number 3. Solve for x. Log to the base 4 of 6 plus log to the base 4 of x plus 1 equals 3. So once again I see that I have a sum between 2 logs, so I'm going to rewrite this as log to the base 4 of 6 multiplied by x plus 1 is equal to 3. I've got a log just on one side of the equation, so let's rewrite this as an exponential. 4 to the third power is equal to 6 times x plus 1. So 4 to the third, 6 times x plus 1. We know that 4 to the third is 64. When we distribute the 6, we get 6x plus 6. So I want to solve for x, so I'll subtract 6 from both sides of the equation, so I get 58 is equal to 6x. And when I divide both sides by 6, I get x is equal to 58 over 6, which reduces to 29 over 3. Again, this is a tough one to check unless your calculator has the option of writing a base. Let's move ahead to example number 4 on the next page. In this case, I see again that I have a sum between two logs, so I'm going to rewrite this as log to the base 4 of 4x multiplied by 3. This one is a little bit different because on the right side of my equation I also have log to the base 4 of 48. On the left side I've condensed. On the right side I've only got one log. So now what I'm going to do is say if the log of 4x times 3 is equal to the log of 48, that must mean that the arguments have to equal each other. So 4x times 3 must equal 48. In essence, I'm dropping the logs because I already have a log on both sides of the equation. So this kind of equation is different from the last 3 examples where I had a log only on one side, because in those cases I had to solve by writing the equation exponentially. In this case I don't write it exponentially, I drop off the logs and solve. So now I have 12x is equal to 48. So dividing both sides by 12, that gives me that x is equal to 4. Now again, you can go ahead and go back and check this. Let me just check one of these. I'm going to check this one a little bit differently. I'm still going to put 4 in for x, so I've got log to the base 4 of 4 times 4, which is 16, plus log to the base 4 of 3. And I want to know, does that equal log to the base 4 of 48? And the answer is yes, because when I have a sum between two logs, that tells me that I am going to multiply together the 16 and the 3. So 16 times 3 gives me 48. On the left side, I also have log to the base 4 of 48 on the right side. So both sides match, and therefore x equals 4 must be my solution. So let's try example number 5. Log to the base 3 of 2x plus log to the base 3 of 6 equals log to the base 3 of 72. Again, addition between two logs tells me to rewrite this as log to the base 3 of 2x multiplied by 6 has to equal log to the base 3 of 72. Now because I have a log on both sides of the equation, I'm going to set the arguments equal to each other, so 2x times 6 is equal to 72. 12x equals 72. So that tells me that x must be equal to 6. And again, you can go back and check and make sure that the left side and the right side both equal log to the base 3 of 72. Taking a look at the last example that we're going to do together, I've got log of x plus 3 minus log of x equals log of 2. You'll recall from an earlier lesson that if our log does not have a base written in, this is called a common log. And we assume that the base of a common log is equal to 10. We're not going to solve the equation any differently, it's just nice to know what the base is. So for this one I want to rewrite, but it's a little bit different because I see that I have subtraction between two logs. So when there's subtraction between two logs, this gets rewritten as a quotient. So log of x plus 3 over x. So notice that I do the quotient of the arguments is equal to log of 2. Now again, when I see that I've got a log on the left side and a log on the right side, that means that x plus 3 over x must equal the answer 2. This is just a proportion, so I can cross multiply. 2x is equal to x plus 3. If I subtract x from both sides of the equation, that gives me the solution x equals 3. So going back to check this one, log of 3 plus 3, which means log of 6, minus log of x, so minus log of 3. Does that equal log of 2? Well, yes, because when I've got division, I'm going to divide 6 by 3, and that does give me an answer of log of 2. So that checks, and x equals 3 is our solution. Now, there's a spot for you to do 2 practice problems in your notes on page 10. So I'd like you to write down these 2 practice problems, pause the video, solve them, and then come back and check your work with mine. Welcome back. Hope you had good luck with these 2 log equations. In number 1, I condensed the logs by multiplying 8 times x plus 2. So log to the base 4 of x plus 2 times 8 equals 3. Because there's only a log on one side of the equation, I rewrote it as an exponential. Follow my arrows to get the exponential equation 4 to the third is equal to, I distributed the 8 times the x plus 2, and that gave me 8x plus 16. We know that 4 to the third is 64, so 64 is equal to 8x plus 16. Subtract 16 from both sides of the equation, divide by 8, and our solution should be x equals 6. And again, you can go back and check that by putting 6 in for x in the original and combining to see if we've got a correct exponential equation. For number 2, I had subtraction between 2 logs, so I rewrote that as the quotient, log to the base 2 of 3x plus 9 over x plus 1. On the right side, I've still got log to the base 2 of 6. Because both sides of the equation have log to the base 2, I'm going to set 3x plus 9 over x plus 1 equal to 6. I cross-multiplied because, again, this is a proportion, so 6 times x plus 1 gives me 6x plus 6 equals 3x plus 9. I subtracted 3x from both sides of the equation, and then I subtracted 6 from both sides. So the solution for this one is x equals 1. Practice by looking over these examples and make sure you understand the difference between the 2 kinds of log equations. Equations that have logs on one side versus equations that have logs on 2 sides. We'll be practicing some more with these log equations tomorrow in class. Have a great night, and we'll see you tomorrow.